I'm going to talk to you all about the Chesapeake Bay Impact Crater. I was very lucky to be working for the U.S. Geological Survey, which I love very much. The organization is one of the best to be associated with, and a great team of geologists. I want to point out before I get going that it took a team really to do this. I was leading the charge because of me being the guy that described the first core that really got the breccia, but I had a lot of trouble with everybody believing anything that I put together, and especially this subsurface mapping that I'm going to talk to you about, and slowly proved it. But let me get going here. This first picture is an image that shows the Virginia pilot did a week-long thing on us when we were the whole procedure, and the lady Diane Tennant wrote beautiful prose. I thought I would start out reading some of her description of what it was like, but I decided I was better to give you more pictures and stuff of various things. And being a mineralogical group, I changed everything today to show you a lot more of the core from the deep Corehole and some of the petrography and some of the thin sections that Wright Horton actually made of some of the melt stuff. That's very cool stuff to have finally gotten to the melt. It's all buried very deeply. And I put the atomic, so they show this asteroid coming in this image from the newspaper, but of course they're not on fire coming in if you know anything about space. The atomic bomb on the right is to remind me to tell you that a lot of our knowledge about impact craters and impacts comes from the physicist studying nuclear explosions. Of course, that's like a firecracker compared to what it makes to a firecracker compared to a nuclear explosion is almost the scaling factor between that nuclear explosion and what created the Chesapeake Bay Impact Crater. And the cross section down there, I'll talk about it more, but that's actually a realistic cross section showing the central peak and the moat around it, and then the annular trough that's outside of that. And then you can see the green colors are the actual, they're fractured and faulted, but those are still sitting there pretty much like they are. And the other contour map there is actually an image showing you from those are depths of how thick when the target hit, that's what was there already. And in the cross section, I'll show later, there's a little dashed line that goes across there, and that's where the top of it was. So it completely cut a big hole in it. But let me just move to the next one. So I'm going to try to tell you about what and where is the Chesapeake Bay Impact Crater, a little bit about the event itself. I normally have a great movie that really takes care of it, but I couldn't play it because my computer locked up today and died. So I'm using a different computer that I can't play it on. It's on a DVD, and I didn't have time to get it over. And then how do we map the buried crater? A little bit about that. That's the mapping. And then at the end, if I have time, how does the crater still affect the region? Because it still has a lot of effects on the crater. In the background, you'll see one of the oceanic nuclear explosions, and you can see the ships for scale. And that's a little teeny thing, but I like putting that in to show that there's an amazing, there is an amazing amount of expansion of the cloud at the base and the waves, and because that's in water, it pushes a wave out. It's got all this other stuff coming down. The atmospheric, I had a guy that modeled the atmosphere, and it looked like the most chaotic thing I've ever seen. Things are going up, down, sideways, and around. And he's one of those guys that studies nuclear explosions. So starting off, there's a long history to this investigation in the sense of all the way back to 1913, because the story ties the impact crater to the salinity that's been found in the groundwater down there since 1913. Actually, before that, it started at and I'll go into that and show you some pictures about the Union soldiers trying to get a well drilled at Fort Monroe, and 5 years of digging, it just got saltier and saltier as they went down. Then in 45, there was a lot of drought, and they were building all the bases for World War II during the war. And so a guy named, who I would say is the real discoverer, without his work, who knows where the Corps still would have made the story, but we would have been very slow to figure out that it was all the story of the crater and where it is. And luckily he published with the state, and he said there was a big hole there and that it was this mixed ages and fauna, but they talked him out of it. He published that in the 40s, and by the 50s, they had talked him out of that all of that was contamination and downhole mixing of the sediments. And unfortunately, he was actually right on it. And I like to say that if he'd had a core of it ever, instead of just cuttings out of a well, he probably would have had the whole story. And the scientists would have flocked to him. Then there was 88 in the 80s, they did major water frameworks and they put a whole thing together, but they didn't know, and they thought there was quite a different framework there. Then in the 90s, I actually finally got to publish this, but it started in the late 80s. And in the early 90s, we were actually pushing that it was an impact as we kept getting more data. And then we actually, in the 2000s, and then subsequently, a lot of different publications. But one of them was a new framework, hydrological framework. Okay, most of you probably know what an impact crater is, but I'd like to put this in just in case anybody doesn't know. Meteorite crater out in Arizona is the first proven crater, because you were considered a heretic pretty much if you believed in impact craters. The survey itself put a statement out, even though personally in writings he thought that it wasn't, but early on they described this as, because it's surrounded by volcanoes around there and lava flows and stuff, they thought it was a cryptovolcanic explosion. So all the craters were considered that. So even about 50 years ago, you were pretty much a heretic if you were pushing for craters. And one story goes in that Thomas Jefferson himself read a newspaper article about these, I think it was Massachusetts, described a meteorite shower, and he said he'd sooner believe the cows fly. In essence, that's not the exact words, than to believe that rocks were falling from the sky. So it's kind of funny that I wind up getting a Thomas Jefferson Award for the crater work. I thought it was a little bit of a misnomer. But the Apollo missions were one of the main things that proved that that these were impact craters and not volcanic explosions, cryptovolcanic explosions. And I like to remind myself the surface of the Earth would look a lot like this if it wasn't for all the dynamic factors that are going on, tectonic and weathering, that goes on the planet. And then lastly, if you've never seen a meteorite or collect them, yeah, look, that white one that hit if you find a meteorite, or if you have a vehicle or a house or anything, do not repair it. You can sell it for a lot of money. I just tell you that. I bought myself for a show and tell, a Gibeon 60-pound uncut meteorite. It cost the cost of a truck. You could sell it for a lot of money. It's now a national treasure, so you have to be careful about in other countries. It was, if you don't know about the Gibeons, they fell in Namibia, and they now have made them all a national treasure there. But I bought mine legally and not from there, from those since they did it. Anyway, we commonly there's activity all the time. We're being hit all the time by stuff, in case you didn't know it, and throughout time. And then one of the big questions that we had, and there's still a debate going on it, is that what hit us? And if it was an asteroid, that's one thing, and it's a comet, it's another. There's been some work over in Italy that's suggesting that they are not not comets, but they are asteroids. And they have a couple of layers separated, so they're looking at both Papagae and the Chesapeake Bay for the sources of them. And there's a whole article on the chemistry and why they're arguing. And there's two different types of asteroids. So I was going to have the references, but you can look that up. It's not too hard. Or I can actually, if anybody asks me, I've got the report on it and stuff. It's just I decided it wasn't the key thing to talk about here. And then in case you don't know, there's a difference between a simple crater like meteorite crater and then complex crater, as shown here, the one on the moon and the cross section up above, where you're hitting, it's deep enough that it hits different rheologies, and so you can get what we call the inverted sombrero, this one up here on the left, in the central peak. So you actually melt the rocks and it shoots back up, just like if you threw a rock in the water. This shoots back up and then collapses back down. And your ejectol shoots out. And then if in an ocean impact like this one, believe it or not, you almost fill the crater right afterwards. All this stuff, the waves rip everything back into it and keep ripping the sides and moving stuff around. And the evidence is seen in the cores. And here's just a diagrammatic image of what the Chesapeake Bay Impact Crater looks like, with a central peak, the inner basin, and this is where we call the Moat, and then the annular trough, and then the outer rim. And this is what I mapped originally, was this outer rim and a deeper hole. Didn't know about the central peak at all. And I also knew there was a bit of the stuff from my mapping outside of this. And out here, we have an outer fracture zone that you can see how it's fractured here in the zone. So the whole thing's 53 miles in diameter, but I'm getting ahead of myself. I'll summarize here in a minute. Okay, when did it hit? Well, all evidence is 35.5, 35.7, 35.4 million. We've actually dated the melt and they've dated some of the little melt particles that have fallen down at various places. And I appreciate Don Davis. He was a big reason that a lot of the NASA got funded, is his great artistic stuff. I talked with him about doing one for the Chesapeake Bay Impact Crater, but he wanted too much money. I'm a poor guy. And then so the shoreline was looking something like this, which was west of Richmond, and you had these eutheriums, and it was a tropical forest because it was a very warm time. Sea level was 330 feet higher than it is now, approximately 100 meters higher, somewhere like I was saying. And then here's the impact site. Let's see if this works. Oh, maybe the video won't work.
Today, scientists believe a comet or asteroid more than a mile wide slammed into the coast where the Chesapeake Bay now sits, forming the largest crater ever found in North America. 56 miles wide and as deep as the Grand Canyon at its center.
We now know it's a lot deeper than that.
Impact. I say, well, it actually happened here. It just happened 35 million years ago.
Just as in the movie, Powers believes the impact spawned a giant tidal wave that reached hundreds of miles inland to the Blue Ridge Mountains, wiping out all life along both sides of the Atlantic Ocean in an instant.
Shooting team ready.
One ready.
Now, Powers is in the field trying to map the features of his amazing find. To do this, the team detonates small explosives along a 7-mile stretch, creating seismic waves that bounce off layers deep below ground. Geologist is busy blowing up holes.
5, 4, 3, 2, 1.
Then back to the surface to be recorded. It's an ultrasound for underground, inside the crater since it was formed. Powers' colleagues from the U.S. Geological Survey have drilled nearly 2,200 feet below the surface to bring up dirt and rock that haven't seen daylight in 35 million years.
We crushed and fractured the rocks up for about 40,000 feet down.
Okay, that was just some clips that I put together because I couldn't show you the real good one, but here's a little more annotation about the same thing. In 0 to 6 seconds, you have all this R11 earthquakes, the forest catch on fire by an infrared flash, and you have a shock wave that goes out and puts it out immediately, and you vaporize the impactor and a lot of what it's hitting, as well as, you have in impact, you have a couple different stages, compression, and you go to, I can't even think of them right now, and I wrote them down earlier so I wouldn't forget, because I haven't talked about this in a while. And you get excavation, and you actually get weird stuff in the crater this big, and then you get all this resurge and stuff because it's an oceanic impact. But let me just keep moving on. Then in 50 to 200 seconds, the atmospheric blast wave traveling probably 160 miles per hour, maybe even faster than that. flattens everything down. So you flatten the forest, and they like to call it the birthday cake effect. And then you have major things up to the size of buildings being ejected all over the place. And some of the stuff goes way up all the way north of Philadelphia and stuff. Then the mega waves come, and it's a train of tidal waves that just go all over the place. You have the central uplift that produces this. You'll see it in the modeling here in a few moments. And the waves discussion, how high they are, is still a debate, but it appears they seem to be high enough to have gone to the Blue Ridge. And people laughed about that a lot. But now the leading theory to explain the biota that they find in the caves out here in the Shenandoah Valley and in the mountains, this is the running theory, the best one I've heard. They still say, Dave Nelms was the one to throw it into their think tank, was that it came from the wave that was related to the crater. And there's more evidence on that, but I find that interesting. Some people have pushed things so far as to say, oh, this thing caused the triple jump. There's all kinds of arguments. And there's some lava that the last lava that I know of that was dated, the last I heard, it's been a few years, they may have done better work now, dates to this. The oil companies, when I was getting the seismic data from them, they were telling me, oh yeah, they have a major heat up event in the deep Triassic basins that date at this time. I don't know if it's major, but they said there's a heat up event. Okay, how did we discover this crater? Well, we started by here at this, where it says Exmore, right here, just inside the edge of the crater. And we were marching down doing a stratigraphic structural framework study. Everything was normal. And we did our last hole here. And we were going to do one here. And we decided, hey, we might be able to skip that one and do this one over here. So we made a deal, an experimental farm over there, agricultural farm with the state. And we cored this hole, and we expected to hit normal stratigraphy and go down, and around 1,200 feet down, something like that, 11 something, 1,200 feet down, we ran into this incredible mixture of clasts of things that we normally see, totally separate in nice layers that are hundreds of feet thick. And we were seeing it all mixed in with this delicate glauconitic grain that normally, if you know anything about glauconite, it's basically like a clay mineral, but it's actually, the best evidence is that they argued a lot through the 50s, all kinds of chemistry, but it seems to be its feces from various animals that set up both the different levels of oxidization that occur within these grains, and they form in very slow sedimentation areas. And it's forming now in various places around the world and at various depths. Anyway, we found it here, and then through the years, and I go through this in the next quite a few slides, of the years that we went from here, and then we were doing cores that were not involved with it down in Dismal Swamp, and another one over here at Fentress, and normal stratigraphy was found there. And then we did this one up here at Jenkins Bridge, and we didn't get to core where we should have, and we got cored down deep enough to know that it wasn't real thick like it is here. And then we kept drilling. I'll go on to the latter drilling. That Langley one is here, but I'll go on and show you some more stuff because I come back to this kind of an image. Matter of fact, here's a good one that shows the names of them. This was the one that I had after this one. This was the next one that I was able to talk them into to drill. And I had to pull a lot of strigs and do a lot of maneuvering to get this core hole done. And we just reached the Exmore and they had to quit. That's another whole story. And what these colors are showing the different units, and this being Crater Unit B, the Exmore, Crater Unit being like the Exmore is all these blocks and stuff, and Crater Unit A being bigger blocks. And some of this still gets the glauconite all the way down in parts of this Crater Unit B. But that's another story. So back in the late 80s, shortly after and this is where I actually want to show, right after this is this one little image. I'll try to hold it up to the camera. But I did a cross section and published it and put it out in 88. And actually, so here's Exmore and here's the Exmore beds. And I'm pointing with my fingers. Oops. Here's Exmore and here's the Exmore beds. We cored this and we cored the top but we didn't get this. But I interpreted from the logs and the other things north that these were the units, and that there was a little thin maybe bit of there from the geophysical logs. The real interesting thing was here, as you cross over from across the mouth of the Chesapeake Bay here, get over here, and this is in the bay, Norfolk, and over here, completely different pile of sediments. You get the upper Cenomanian beds, and you get some of these older Paleocene, upper Cretaceous units, and the Paleocene, and then even the Eocene. And then you have the young units, and you're missing all of this stuff. So something was going on that needed to be explained. So everybody liked it that there was a fault here, but they didn't like it. What I did here is I'd actually, I don't know if you can see this. There's enough light. Let me do this. But there's this is a 3D image of what I did. I contoured all of this. So it was, and believe it or not, where I had the edge of the crater all the way around in a semicircular area, what turned out to be exactly where the seismic and the core holes have proven it. And I did that all based on the water well data. And everybody said, oh, you can't use that. Same argument against Cedarstrom. That's not, you can't use, that's contaminated. You can't use it. But I went through it and went through it and went through it. And vacation over, every weekend, every night, hardly slept, and kept fighting it, even prayed to God about it. And 3 a.m. here on the floor, I finally had the eureka moment and said, I've got it. And here I'm working with all these maps and spread out all over several rooms, books and everything you can imagine open everywhere. And I kept compiling, and I said, I've got it. They're going to have to prove me wrong, not that I have to prove that to myself. They're going to have to say this is not right. And so then we drilled all these years in the 86, 87, like I was just saying, and 88. And the 89's when I was able to talk him into drilling at Kiptopeke. And when I talked Scott Bruce, the State Water Control Board, to do that, and they turned a water well rig into a coring rig, and really did remarkable stuff with it. We hit that, and so then people started believing me a little bit, and so he agreed to go back to one of the earlier holes at Newport News that they had drilled. There's a whole story behind that I'm coming up to. So this is a picture of the Exmore breccia right here, and this is a crystalline clast, cataclastic clast, actually. It's all messed up. It's found within the breccia, but see the angle of that? And this little shell fragments in here, and another little class of something else, another class, different class up here, little pebbles, little pieces in here. Well, this is the stuff. This is what we call the Exmore matrix. It's glauconitic, it's got everything. It has little pieces of melt in it. It's got shock quartz in it, but it takes 1,000 pieces. So when we cored Exmore in 1986, I had 3 theories, and one of them happened to be that it had to come from an impact crater. The other 2 were that it had to be like a paleo valley, and there was an earthquake and everything fell into it. It still kept it marine and didn't move very far, because the glauconite would disintegrate if it went from 100 yards in a movement, but generally speaking, unless it was a big block or something. So we were coming, and then the other theory is that there was a paleo shelf that we didn't know about, that slumped, and all this was like a talus slope thing that came down there. And everybody had a good laugh at that it might be a meteorite crater. I'd been exposed to meteorites through Danny Milton there in the office, and I actually used to think, because he was doing such cool mineralogy, I thought it was kind of esoterical that he was so crazy about impact craters at the time, when I was going around meeting everybody and learning different things that they did. This core on the right is actually, these are both from the Bayside Corehole, which was later on in 2002, I believe we drilled it. This was the stuff that's above the basement, and it's argued that it's actually a ground rubble that was produced as all the floor of the crater out in the annular trough was being eroded and hit by the tsunamis and everything, the Resurge deposits. In 1992, actually Larry Poppy found the first proof of the impact from some of the cores, and he found what is called shock quartz. And if you know anything about the impact crater mineralogy, these high pressure minerals have not been found on the planet produced by anything else. And you see the striations that go different angles here? Those are deformation features that prove that this was produced by these incredibly high pressures. You can see that 300,000, 600,000, 20 pounds per square inch. That's a lot of pressure to produce that. But there, 1 grain in thousands was found. In this picture, I give credit to Glenn Izett, who found this out of the Langley Corehole core. And Lucy already gave you a talk about the dinocyst damage. It was the first time ever we found that the dinocysts were actually melted and fused, and so that gave us a new key for other people to look for. If you see some damage like this, then you may have an impact crater involved. The nanofossils also, gene cell trail found, were broken and fractured and had impact damage as well. Now, part of the story goes back to previous to this. Back in the early 1900s, they found some of these microtektites way down here in Texas. And they called them betasites because they was found close to a town. Then they found them in Georgia. Then later on, they were doing deep sea drilling and they found the microtektites down in these cores. Then in 1983, they found them in Site 612. Wiley Pogue was on board in charge of this study, and they proposed that there had to be a impact crater close by. And he actually proposed later on there was the Tom's Canyon crater, and was convincing me that the Exmore was actually just a tsunami deposit from that crater. So we published that in 1992. And Wiley was brought in to study the Exmore for the forams. And Lucy Edwards was working on the dinos. What's interesting is Wiley came up with it. It was Middle Eocene, and Lucy, it took a little while, but she came up with it was Upper Eocene, and then Wiley found the Upper Eocene. But for a couple of years there, I was putting out sections that it was all Middle Eocene. So it took a little bit extra work. But these tektites now, there's been arguments that they're found a lot further, and like they're arguing again, it was up that they were there in Italy, and now they weren't, and now they're being argued in more recent publications that they are there. So they may have traveled much further. But in case you didn't know it, there's a sister, almost the dates at the same time, only so many centimeters apart in the deep sea sediments, that over in Russia, there's a impact crater called Papagai. And it's all on land, and it's much bigger crater than the Chesapeake Bay Impact Crater. And it was used to argue, along with some of the other Upper Eocene impacts that are around the world, that this may have been a comet shower. Matter of fact, Eugene Shoemaker gave a beautiful talk at the Cosmos Club describing how he thought it was, and had a theory about, every 35 million years, our solar system moves through the central part of the Milky Way galaxy. And so that was producing, I thought it was pretty brilliant. And there is a periodicity to it all. So he had to go in. And so it's a great one when you're teaching students stuff. Okay, you teach them this, and they had 35 million years old, and then the dinosaurs were killed off 65 million years ago. So I get them to come up with, well, when are we expecting another one? And they say, now. So we might get another big one anytime. Here's a quick thing of the marine impact craters around the world. And this is considered, it was back when I made this slide, it was the 7th largest. Now I think people are putting it in the mid-teens. They keep finding more craters, of course, now that we're looking for them. And then here's just an example of the number of boloid events in 1994 to 2013. Most of them disintegrated in the atmosphere, but matter of fact, I've had people tell me they've seen explosions up there that people have say they're part of something hitting the airplane pilots see them occasionally. I put this in just to remind myself that we did more than just seismic and cores and looking at the borehole data. Now, when I was looking at all the water well data, there was a guy named J.D. Cedarstrom I mentioned before that did a lot of mapping, and he published with the state actually lithic descriptions, and he described he would sit on the wells and collect the samples. So it was quite well done. And he was relating that the basin had something to do with the, it sort of tied in with the salinity story they were finding, which was somehow it went right where the crater is, it went far inland. And so they called it the Virginia Inland Saltwater Wedge. And I've changed it it's a mound. It's a bulge. It actually sticks up higher as well as going inland. Anyway, we did some other types of geophysics, and we ran things called AMT and MT, which is the audiomagnetic telluric or magnetic telluric. The audiomagnetic telluric is a kind of, you put these probes in the ground, not very deep, you just bury them slightly and leave them there for a week or 2 weeks. And they're so responsive to the electrical resistivity that if a light is turned on in a house within a mile, it notices that. And what it does is it uses lightning strikes from around the world to send to one direction momentarily through the earth, and it sort of that we use that to tell the resistivities and various things, structural and resistivity. It worked real well for the craters, the outer rim, because of the fresh water outside and the saline water inside that outer credge. And so we did that, and then we did the MT, the deeper stuff, which actually uses the ionosphere's wobble. And you can see you make these, it's pretty much black box. How you have to process all the data. And the problem was he had to have a model to put into the whole thing. And of course, the model's my cross sections. This is an image just to show, and I show this more than once, I'll show it again, all the seismic data that we got. We got the red lines are the oil company lines. This is 1CB. I will show you a piece of that right here. And then USGS, along with National Geographic, we got some more line. They went in and ran more lines. And then we did on land high resolution seismic data here and down here. And we did AMT data down there and there. And then we did, to get the money for the deep core, we had to do a deep seismic line here, 30 kilometers long. One little owner wouldn't let us in. And another one that crossed here. And each of these blue squares where we did high resolution seismic. And we did a cross on the Corehole. That's where it is. And it was very helpful. You know, I just did this again. That's right where we're going to be seeing this next section. This is the oil company data that was released, and they only gave it down to me. The reason I was able to get it is I asked for from the basement up to the top, and that's called overburden to them. It doesn't give them anything or anybody else information about the oil or anything down below. And first time they sent it to me, they cut it right between this reflector. The next time I was able to go down and I talked them into cutting it just below that, because that's the double reflector that you get at the top of the basement. And what you can see is here you are going across here. And if I'd shown another one, some of this where we see double reflectors may be, as we show in a model here, that you're actually getting some of the flap. When this thing, the basement opens up, it actually will fall down. But because it's a ocean resurge and there's so much going on, just tearing everything's moving, as you'll see in the model, that you only get little pieces left. And then right here, you can see, here you are dropping into the real part of the crater that's the hole in the crystalline. Right there, you're already down, 1 mile. This is our Exmore, this is our Langley Corehole here. And one of the key things that we had to get to be able to do a better job with the seismic data was to get a sonic velocity log. So this was our first good sonic velocity log of the crater, within the crater. And what you're seeing is higher velocities here. You're seeing the basement shooting way up, a big change right there when you get into crater unit C. And here's that's actually the top of the breccia. So the Exmore, you can see the variations within it because it's mixed with so many different things. And then the post-impact is almost like water. It's very light, a little bit of hard stuff where it's cemented. But that turned out to be very useful in how we interpret. Because when you're working on seismic data, here's normal Bayside Corehole depths, and it's not very far from where this end of the line is, 6 kilometers in southwest. This is what you have to convert that to this to two-way to this seismic two-way travel time. What I want you to notice is that when you're working with seismic data, as you go down, the same thickness, like from here to here, is now only like the thickness of that black line, to be equivalent to that same thickness. So the deeper you go, the thinner it is to be more depth. So whatever your unit is, in reality, you have to rethink it that it's going to be down here lower. So this is the top of the debris, this red. And then you get these nice, beautiful layering and some faulting in there, and faulting, of course, fracturing there. But that helped out. So here's the summary about, did it kill anything? Because I'm always asked about that. I know I'm jumping around. I'll come back to the seismic. But yeah, it killed everything within, many miles, up to, 160 miles. It did a lot of damage to stuff that close to it. And the tsunamis swept everything from all over the place, but it didn't kill off everything. Before this impact crater, the theory was that anything this big could be a planet killer, or cause at least extinctions for sure. And we don't have that in this. And the argument was that it proved that it really depends on what the target hits. And this is almost all siliclastics being thrown up into the air. Very different from the dinosaur killer, where you were throwing sulfides and limestone and gypsum, all kinds of different things up, very different. So you could actually create an acid rain that helps destroy the bone bed of the kill-off. Anyway, that's a whole nother story to get into that comparison. See, there's no major animal or plant extinctions. So far, just to sum up what we have is that, we got an Eocene impact. The thing that came in based on the modelers, they think 3 to 4 miles, 3 to 4 kilometers or 2 miles in diameter. The speed could have been up to 162,000 if it was a comet, but more likely it was in the 30,000, 40,000 or something like that miles per hour range if it was an asteroid. Mentioned about the shoreline being so far west, and that it actually penetrated 300 to 600 feet of water, or that's actually, I think, yeah, that's about right. And 2,000 feet of sediment, and it blasted its way into 5 miles into the basement rock or more. I think it fractured rocks all the way down to the Moho, actually. We have a little bit of data that we never did get published on that. Hopefully we can someday. Although I'm not working on any of this stuff for a long time. Haven't talked to anybody about this for a while. The outer rim diameter is 56 miles in diameter approximately. And outside of that, there's a disruption boundary where you finally stop in 85 miles. Now, this is another argument, is how tall was the splash? Well, the modelers and the physicists tell me it's 30 to 35 miles high. Chicxulub was 50 miles or more, 50 to 60 miles tall. And there's arguments on how high the wave was, because gravity brings it down. So maybe it was 1,500 feet, maybe it was 2,000, maybe not. We also did gravity surveys, and that's another way to find craters, is you knock so much out of there, there's a low. And if you have a circular low gravity, you might have a crater. These yellow dots are where we actually did little gravity stations. We did them on the islands. We did it on, you'd be amazed. Some of them we did on all kinds of little sandbars and stuff. And then they did some marine survey out there. And then they added all that to the pre-existing gravity data. And you can see here's the central high, is the low in the Moat, where the most of the basement was knocked out. And then these highs wrapping around the central crater. There was the magnetic data done by Angie Shaw, and compiled it she did work on the cores from the deep core hole at Airville, it's called, which is down here at the center. That's the story I'm going to mainly show you. And these red things, she believes from her modeling, indicates that they're either giant crystalline blocks that are very magnetic, or they are spread out parts of the melt sheet. Back to the gravity survey, just wanted to point out, this is where we did our deep core hole, and we also tried to do a deep core here before we did the deep one at Cape Charles. And we put in a sampled water well data, and the salinity in these things is off the charts. You're into the brine world. Wanted to put this is down here where this survey is crossing from L to W, and this is outside the crater, and this is in the crater. This is resistivity, so the higher resistivity showing the fresher water. Well, this is along the rim of the crater. Here's the rim. And then, so this suggested that the fresh water was actually going up in the fracture zones through the clays and the layers, the normal layering, and come up here and then spread out across the top. So this is where they can get fresh water. Of course, it's close to where it can get contaminated. See, it's 100 meters down. Down here, no luck. Not going to get any groundwater, not to use. This just shows a detail of the 30-kilometer seismic line we did. We crisscrossed the airville hole. We did this cross line. When we did this, we really went straight as possibly could be. We cut through fields. I had to go and get permission from all these people. That was no small feat. This is a rural community. And if you make a mistake with one, you've made a mistake with all of them. And so I was very fortunate. I'm pretty well known over there. People say I could run for office and get elected. I'm known as the crater guy over there, which is pretty weird. But we did all this. We cut through. We actually did things in the water. We bought these long poles, and we would attach these standalone seismic Texans to each one of them. We did have a problem after we ran this, and this took army of people. We had all these people and students from Virginia Tech, and all these people from California came to help out. And when we finished, we came back, and they said a bunch of them, we were bringing them back, and they said a bunch of them didn't turn on because they were all timed to turn on, and they'd made a mistake when they were setting them up. So I passed out on the driveway. I thought I hit my head on the concrete. As a matter of fact, they thought I may be dead. And they just said, "Oh, we'll just do it again." And I said, "You don't realize what it took," because on top of the seismic, we did for this one, we put in all these holes. We drilled wells down to 75 to 90 feet in PVC, and then we loaded them up with, just before we shot, we loaded them up with all this plastic explosives, and slowly went from here all the way up, and then did from here over to there, all in one night, early in the morning, and would have to go from site to site, blowing them up. And I actually have a cool video that I've shown to people that summarizes all of that, and it gets pretty exciting. You hear all the explosions, and the trees are falling, and we found out from a test hole that we don't need very much explosives. It really propagates this water-rich pile of sediments, and the crystalline rocks really propagate the signals very well. In case you've never been over there on the Eastern Shore, and here's Cape Charles, this sort of the south side of it up here is where we drilled the Cape Charles test hole. And the central peak, so this is sitting on part of the central peak, is running along parallel to this shoreline right here. And as you move up here, you're going into the Moat. And we cut our way through all this stuff, and cornfields and cotton fields. And one place we went through over about a mile or two of nothing but thorn bushes. They were 10, 15 feet tall. We're hacking our way through tape measures, and because we were in the woods so often, the GPS wasn't very good. I put this in just to remind myself that I got a chance to go down to the oil companies and see the entire data. And so this was a tracing I did of the central part of the crater. And it shows that by the time you're down here, let's see, I think by the time down here, you're 8 or 10 miles. So you're way down there, 20,000 feet, about in here, something like that. And this is where we put that deep core hole. We did velocity modeling. I just show this on the long seismic. So the deep core hole is down here. but it shows that there's a lower velocity when you step into the central crater and much higher right outside it. And then this is what the seismic line looked like. So the main thing here is when you get to the green, you're entering into the Exmore. And these are the post-impact sediments. One thing to note, just as I had mapped early on and saying all the units, the post-impact units dip in towards the crater and thicken and deepen as you go into the crater. So we think this is the crater rim, these higher velocities, different stuff. And then biggest thing to get out of this is we drilled to here. Much of us have argued that this is the base of the crater, and that if that's true, and that's what we finally published later on, was that we only got through half of the pile. If not even that, we went from there to there. So we got through, of the debris itself, a quarter of it maybe. And we were into the melt rock and crystalline blocks here. Very exciting to work on that Corehole. Here's the velocity model over top of those various units, just to show you the relationship of the crater debris that we were finding and the velocities. Kind of similar here, but they do drop off into the crater. Here's that magnetotelluric data where you're seeing low resistivities in the moat and higher resistivities on the central uplift, and over here at the raised rim, a little bit higher right there. Just put that in because we actually had the data. I don't think we ever published it. Then I put this in to remind myself that what's the size of our crater compared to some of the others? Here it would be. So one way to think of it, what created the meteorite crater would be a P. It's that little dot. A P created that. A hard ball created this, and a basketball created this one, 10 miles or so in diameter, something like that. Just put that in for size demonstration. Now, if I can get this to work, this is the model that I was hoping to work for you. Oh, I got to do something here. There it goes. See the things popping up and down in the center? That's the central uplift going up and down. And here's the Resurge coming back in. And that was the big wave that went out. And these are pieces of the flap that broke, very much like our seismic. See this sliding in? There's the time code. This is 900 seconds. So everything happens in a few minutes. 6 or 7 minutes, you've done most of the stuff in the crater. Although things kept going on for a while. We actually have evidence out on the west side where even the post-impact Chickahominy slumped into it and wound up with being buried in the debris, and it was post-impact. So you had some things where that outer wall was still playing this outer wall was. Well, I'm actually talking about way out to the outer wall for the sediments were still slumping, not this crater part. This is just some examples of what was happening here. There's the chaos going on in here, and here's the big wave and the flap going out, and you overturn flap, 1.5 minutes, and the Resurge comes flying back in, and here's an example of this is all fractured and knocked around, and everything. In other words, I like what Goen et al. Said. Actually, Greg Goen said he was the project chief on all of this, and he said you can just about anything you can imagine happened in this crater when it was formed, and I still like that. Going back to the legacy, here's Cedarstrom. I still give him credit. Drew Ming, myself, Scott Bruce down here. Scott Bruce again, and Randy McFarland, he was the publisher of this. He took over what I initially was doing. Now, one of the things that happened is when I was working to try to get this going, I wound up, after I even got the seismic data, the people down here still didn't believe it. Back both at the survey, that this was the crater, and they didn't believe there was this wall here. The consultants all said it wasn't, and they were telling me you can just take this paper and use it for toilet paper because once we core that hole, it'll prove the whole thing's totally garbage. The idea of it all. And when we drilled coral, the Langley coral, all those consultants came over and had a good cry, and were unhappy that I was so right. They came up and said, "How come you're always right?" I said, "Nobody's always right." And I felt more like I'm more like the guy. This is the Wizard of Oz behind the curtain pulling strings rather than anything magical. I just stuck to my guns and said, "No, this stuff is the way it goes." And Cedarstrom had mapped stuff, and he called it he'd mapped this whole thing and he named it the Mattaponi. But when I did my subsurface mapping in 86 and early 87, I saw that what he'd done is he'd mapped it all over the place. There was a place where his coincided with what I had found, what I was pushing as the Exmore, but a bunch of it wasn't. And so I didn't use the Mattaponi because he had a bunch of the places up to the northwest that I don't see it, and further west, I just didn't see it. But his stuff was right on it. Now this is in a picture of the old cistern, and I'll go quickly to it down at Fort Monroe. See, one of the large cisterns that they used in 1834. They tried to drill this hole in the 14,900 feet deep. They couldn't get it, so they still used cistern and brought water from the wells on the mainland. These are the first guys that had a chance to actually find out there's a crater. And so this is a map. You can't see it very well. So I took the same lines. This is Samuel Sanford's 1913 publication. He's showing that they started following where the salty water was. And it's these dotted lines you can see. And here they are marked a little bit higher, 2000. So it's not too crazy there yet. But then Cedarstrom, he started getting more and more wells and more data by the World War II. And he developed the wedge, and sure enough, it relates exactly to where the crater and the breccia is to the most part. I would say, if I can get this little extra stuff here, although I've always thought this may be, and there may be some breccia here, that this is a product of the crater and structure faults. And there's a big fault. That's something I forgot to mention is there was pre-existing structures and geology here beforehand. And when you hit with a crater like this, you hit it, you may reawaken things that have gotten quiet. And I believe that's what happens in the James River here. And so I've called it the James River structural zone, not just the edge of the crater here, but there's actual structural zone. And that things are very different. The world is different south all the way up to the fall zone than it is to the north, geologically speaking, before the crater and after the crater. There's a lot of differences. Back to the groundwater. I published in showing what the groundwater was by the Drew Ming's framework, RASA framework study. And so you can start to see we're getting 5,000 and stuff. And they actually added one well down here in Norfolk, and the Cape Charles well, the Air Force Base well, they were even higher than that. They're up in the 25, 30,000. I put this in to remind me that the studies that complemented what I was seeing, because one thing is to see the different lithologies, you have to prove their ages. We really had the different mixed ages. And even though I'd be familiar with it and I'm good at, this is that, this is the Marlboro clay, this is you got to prove it. So the foram and dinocysts and the nanofossils and stuff, they were all very helpful. And the people that worked on them, and the pollen, I didn't even put any pollen in here, they were essential to the studies. And so every step along the way, I was working with others to figure the puzzle out. Again, back to the seismic profile, just to remind me, I 8 miles down to the bottom of that. Now, the Papa guy, if you were to drill, and that's an image of it, it has a nice surface image here from satellite. You can really see it. So it's a big crater. And it's eroded down, so it's not pristine and uneroded like the Chesapeake Bay Impact Crater. But here you go. If you were to core a hole, you'd be drilling down through this stuff, and you go through a block, and then you go back into this mess, and then go through another block. So that's what we're really doing. So this is a great example because they have exposures there. What a great place to go. But it's way up there on the north end of Russia. And it's very difficult. We now have quite a network of cores all over Virginia and they're borehole geophysical logs, and it really are useful once you have the cores and you have ground truth. And that's been the key. When we developed this coring program, we changed so much of the framework everywhere we would drill. Once you get that ground truth, all of a sudden you can reinterpret. I'm still mapping over in Maryland, and I'm Washington East. I have spent 2 months going through the database that I had done years ago, because I got some new information, and I'm still trying to document it in a more thoroughly way, because I had thrown it together in a rush, and now I've got a real documentation on that. Now I'm going to try to, this will be a fairly quick pictorial. This is going back through some of that drilling history. This is an important part. In 1983, the same time that Pogue was out there drilling the 612 and finding the Microtektites there, Rasa was drilling some spot cores, and one of them was at Newport News Park, and they drilled it in 83, and they drilled another one in 84 up into Gloucester, the next peninsula, and they submitted their samples, some of those spot cores. They just took a little core every, occasionally. And they have to do that because they weren't really coring. So they'd put a core rod on their drill rods and go down and take a 10-foot section, and then go back to normal drilling. So that's these two spots, Gloucester Landfill and Newport News Park. And this is where Lucy Edwards got into the game. And this is her ER report back to them in 83. And she did 13 samples, and she describes what's going on here in all of this. And some of it was some normal. She could actually give you a pick. But this is what's important. The two things that I covered up in red, because I should have known better than to process this. What looked like such a nice contact was the contact between the downhole trash and the real core. Well, that wasn't even correct. And it would be meaningless anyway if she gave her the floral list. And so she had a chance to be the first one to say, this is it. And I don't believe she knew about Cedarstrom and his mixed fauna that they talked him out of. It was also there in the York James Peninsula. But so this put everything on ice for a while. And it comes back to it that when she looked at the stuff when we cored at Exmore, wow, all of a sudden it didn't really click at the moment that this was it. But after I got it at Kiptopeke in 89, and we went back over to re-drill the Newport News Corehole. We actually did that in 90, I believe it was, yeah. Right after we did the 89, yeah. And we proved that it was there, and then it was a shoe-in that we knew what it is. Here she is. I hated to do it together. You see, we say, so pick your favorite age and interpretation for the samples. So I like that story. It's always a good one. This is a picture of the actual first corehole site at Exmore, and it shows the drillers, and I'm naming them there and everything because I really give a lot of credit to these guys, Don Queen and Dennis Studi. Dennis Studi's on the rig right there. He wound up leaving us for mobile, so he wasn't with us through the whole study. This is Don Queen. He's still alive up in New York. Scott Bruce and Jay Owens and John Greason. And you'll see them over and over here. And there's some of the breccia. And here we are at Jenkins Bridge. We did this in 87. The same guys. And that's when we only got to core the top. And I had to really finagle to get him to core the bottom, bring him a core bit to pull it off. And then this guy died on us in 2005. And he was an old time driller. He was one of the best guys you'll ever meet. Here we go. We drilled at Fentress. Again, we found all normal, like Dismal Swamp I didn't put in here, but then we drilled. Oh, and that was just about how far we were driving. Never mind. I didn't mean to leave that in. There's those two guys. They did it at Kiptopeke. Now, they got that stuff, and I was jumping around. John would say he loved drill for me, because he said, I've never seen anybody get so excited about dirt. And here's an example of the breccia that we got from Kiptopeke. And then they did some real good water quality samples, and the chloride content was 25,000 milligrams per liter, pretty high. So we were tying the story together that clearly I kept saying, well, there's a relationship of Cedarstrom's saltwater wedge and this big hole. And sure enough, it proved out. Here we are at Newport News Park when we cored it and got the breccia again. There it is, Newport News Park 2. Always looks the same. Now, once you've seen it, then you can recognize that matrix and the clasts in it. Then I was able to talk the USGS into drilling one up to prove my northwestern corner of the stuff, just outside the edge at Windmill Point, there at the southeasternmost tip of the northern neck of Virginia. And we were drilling on the Gulf tee, right on the ocean, as you can see. And the northeasterly came in and buried the whole front end of our truck in sand. There's the good old breccia again. Beautiful, beautiful cores. Then we drilled a 1995. I was able to drill one more to prove that things are all normal over here out to the west, a little bit further. And sure enough, Jamestown, we got everything in normal position. And here's the crew that was working. Jerry Johnson was another colleague of mine that worked with me throughout this and was a great help and guide and a conversation. And he knew a lot of the shallow geology better than almost anybody. Then we went through the 2000 to 2004 drilling, all this before the deep Corehole. And we actually had the Rocky Mountain drill team come in with Art Clark and his crew mixed that worked with us, because this was all 24-hour drilling. And there's a story that goes into that I'll get to in a moment when I get the slide. Here we are at NASA Langley in 2000, and that's where my neck was out. Everybody was saying, oh, this will prove how wrong you are. And it proved that I was right on. And my cross-section, my picks for even the post-impact were all within a foot or two. One of the only ones that I was off was there was a fault, and it repeated the Chickahominy section. So it was thicker. This is just an example of some of the main guys. Jean, she worked on the nanofossils. Greg Goen, the project chief. Scott Bruce, these are some of the NASA guys. George, I can't even say his name all of a sudden. And Rob Weems, if you happen to know him, Dave Nelms, Randy McFarland. This was a student working with us. And then me at the Langley site. Oh, there they're all named. Or who they were. And there's some of the core, some kind of this was a metaclastic thing. What was funny is this was a piece of granite, and it turned, the longer it was on the surface, like almost everything, if I was to tell you about everything, things change color in a moment. So if you ever came to a drill site, what you'd mostly see me either describing the core or photographing it or cleaning it. It's a big thing about cleaning the core. That was something we developed. And some people would get upset. They'd see me with a hose, and I'd be washing the core, and they say, "Oh, you can't do that." And I said, "No, I know what I'm doing." And it dries very well this way. When I first came on, they said, "Oh, we slap everything." They would barely see what's in there. One knife cut, and then put it in a piece of plastic and seal it up. And that was the worst thing you could do, because then it would all mold and do bad stuff, fall apart. North Park and Ride, that was one of the core holes we drilled, along with, here it is. We actually had two rigs running at the same time. And up there, you can see the kind of bits. We actually core where we spread it. These are all diamond bits, but we actually use a Christian system where we push the core barrel out in front of that. And so it's almost like split spooning, but you're cutting and pushing at the same time. And sometimes that doesn't work because you hit something hard and it'll take that core and wrap it around the outside of the end of the barrel, and you got to trip out and start all over again. Or not over, but start a new string in there. You also get your core rod stuck. Boy, if you're not watching it, they can get stuck so easily. Matter of fact, we buried quite a bit of core out there. Almost every group of drillers did, including at the deep core site. And there's some cool name, Exmore breccia again. And then the Bayside core, and here we were again, right on the water. And we were going to drill much deeper. A lot of these holes were going to go deeper, and here's the core there. Here's one of those chunks of granite. And it would eventually turn white. See, here's those angles again. Get these sharp angles because you're cutting through boulders and clasts. And then we did Watkins Elementary School to anchor the seismic line. We did a high resolution seismic line from Langley over to where this core was drilled. And sure enough, we got the Exmore there, but a thin, like it's supposed to be on the outside of the crater. Then we did the Cape Charles hole. Here we are. And the Rocky Mountain drilling team did it. And it's the first time we got down deep enough and we got to some of the melt. So here's the first matrix of the melt from there. And there's like some of the melt. You can see it's sliding along. Most of the glass turns to clay, and especially once it's gotten to the surface. These are all shots of there at Cape Charles. Now we did the deep drill hole, and 24/7 for like 3 months. And Major Drilling came in and was the driller, and they brought this rig in. They had to cut stuff off of the thing to get it through the tunnel. It was too big. And then they built this big thing, and they had just come from drilling gold out in Nevada. They said there was a mountain of gold out there. And this rig actually had the record for the deepest borehole in the United States, I believe, or North America possibly. Anyway, they were good drillers. They worked really hard. And so here we found 444 meters of post-impact sediments. And then we went through 900 meters or more than 900 meters. Well, you can see it's 1,200 meters of impact debris. We got down to 1766. We planned to go to 2.5 or 2.3, I'm forgetting now. And you can see a list of some of the various agencies that were helping us. We had an army of scientists and impact specialists from around the world that came and helped. This is just a picture to show these drillers really worked hard and knew what they were doing. But right away, they got the real expensive rods, the real big ones. We were taking PQ core, really big core at first, and they got stuck. And so we wound up having to drill. We kept drilling smaller to telescope down all the way, and we went to a HQ after that, and then went down to NQ eventually, because things kept getting stuck or kept getting stuck. We used a lot of drill mud and a lot of spent a fortune on the chemicals, keeping the drilling mud correct. And I put this in just to show this little bead right there. We were finding what looked like microtektites in the core. And I dug some of them out, and some people argued, oh no, they got in there from the drilling mud and what we put into it. Not it. And you'll see a thin section of one of them later on that Wright Horton gave me a picture of. And other people have published that they did find them there, but I was told I couldn't do it. I've got some beautiful ones that I got out of there in a little vial someplace. So the Airville core located between Cape Charles and Eastville, total depth 10,000 feet, total depth. That was what we wanted to get to, and we only got to 5,795 feet. It was in the Moat. So here's that image at the very beginning I was showing you. And I was making the point that there's a dashed line here that's top of the pre-impact sediment surface. It's actually shown here. And so it knocked a hole, keeps on going down here. Here's the central uplift. And these are I'm going to show you pictures of the core from various parts of this. A little bit of the post-impact, but mostly a little bit of each of these sections. And believe it or not, we went through a giant granite, big block of granite that everybody wanted to stop coring on. I mean, they were ready to really stop. And I kept telling them, no, go. Actually, I had a dream that we would come back into the sand, and we did. Down here, more of the sand. And I felt pretty good about that. Wait a minute. I put this in a second time. I'm surprised. Am I going the wrong way? No. Yeah, this Here we celebrated reaching a mile deep. That was exciting. And that's where I would be. I'd be sitting over the core, photographing box after box after box. And they became the official photographs for the, and published for the ICDP. We take the boxes off site and built these things and had these in the garages of the places that we rented. Oh, one other thing there. I would put show and tell. I had quite a little, I'd take one of these trailers and made it half of it full of core display and posters and on. And people would fly in, rich people. We were trying to get more money from anybody as we ran out of money, and they would bring them in and I'd show them and stuff. And they were crazy about the granite. They said they'd love to have a table of the granite. First run was in 9/15/05. See, that's how big the core was, the first stuff. Really nice. So we got great core of the post-impact section. Actually down into the breccia. We lost that hole around 1,800, 1,900 feet. And the sad thing was, I think, yeah, I think I went home for a moment when they lost the core. Yeah, I think I went home for a short break. I hardly will ever left the site the whole time. And here we are just sampling and cleaning the core. See, I actually cut the core and scrape it and polish it or shine it or wash it, and can actually make it look so it makes for a better photograph, you know, weathering out a little bit. And I put this in to remind me to tell you about the size of the clasts. I don't know if you can see that, but the red were from the first hole that we lost, and we went back down and it deviated and made a whole nother hole about 3 or 4 feet further away. These things don't really go straight down. And these are the sizes of the clasts. This one's up to like around 50 meters. Most of them are 20 or 30 or less. And the blues are all from the second core hole, and we overlap. So we had duplicate core, which was very neat because we could compare what the core was in one to the other, and we could see where the big blocks, it was the same thing, but otherwise it was a completely different pile. So that adds to something that I've always said is every time you core something, it's going to be a different pile. You're going to get a different story. Ultimately, we published what I call the phone book on this. It's a big, thick, you can use it as a doorstop. Professional paper, special paper 458, Geological Society of America, and 42 chapters. I'm on way too many. I worked on so many different things, it kept me from thinking almost. And I wound up only senior authoring the high resolution seismic data that we did at the site. Here's some pictures now. I'm going to go through these quickly. I was going to stop for questions, but I know the time is going too slow. Let me just run through these fast. This will be a picture show. I put this in just to show sometimes we get sands that we call sandbox core. It's a round shape, but then nothing will hold it together. But this is more typical of the post-impact. You see the same sand or clay or shells back and forth, very continuous, no clasts, no weird angles. Here's the type of shelly clays. This is typical stuff. You can see this 4 or 5 down to 400 some feet. Now I jump down to where you're getting to the bottom of some of the older units. Here's the Glock kinetic Oligocene on the left, coming down on that browner Chickahominy formation, which is a very foram-rich clay silt. And it's very diagnostic everywhere you see it. I saw a core up in, before we drilled this, many years before this, because I'd seen Chick already from my earlier drilling at Exmore. Looking at the cores up in New Jersey, I was able to tell them the Oligocene units and the Chickahominy units just by looking at them quickly. And it proved to be correct. Now here you're looking at the very, very top of the Exmore. Whoops. This is the Chick coming down, very fine grain, very consistent for, 100 feet or more. And then right there, it changes to this chicken wire looking thing, more like a shale. Believe it or not, these are all individual little clay silts, laminae. And this is the final settling out of the whole water column. And you hardly find anything in there that's living. It's pretty much, this would be Wiley Pogue's dead zone in here. And there are some different interesting things they find there as far as possibilities of microtektite things that have been changed to pyrite and other byproducts of somehow being altered. Here's where we did the high resolution seismic cross. And here to the left is one of the seismic lines. This is all the base of the post impact goes on up further. And these lines are this uppermost Resurge deposits. You can see they're actually imbricated here and cut over one another. Those we believe are results of the oscillations of the Resurge. And I'll show you in a moment how each one represents a finding upwards package within this. And then down here is total chaos. These are the blocks that I've marked that we went through here and where I think they fit. And then out here, pushing it a little bit, I'm trying to interpret where the green is actually where we find the matrix with the green sands and all the way down to here. So this being the lowest one, we stopped the Resurge, reworked, and then we call it avalanche. But see, this green sand this stuff still gets into here. And there's arguments on whether it's injected in after that's in place or whether it's all kind of mixing in a little bit in the movement earlier on, different pile of sediments. Here's what I'm talking about. At the base, it would look like this, and further up, it's finer grained. And each one of these correlates exactly to one of these, correlates to these lines that you see. So 1, 2, 3, 4, 5 right there where we went through. Now we're down in the sediment class breccias, and it's more class supported. And I want you to notice here, look at the angles. It's nearly vertical dips, angled. You can see the beds dipping there. And then you get all these different class. You start getting these red paleosols from the Cretaceous. We found those in every core, though. Here's more just chaotic mixtures of sediments all slammed together. It would change, and that's the examples of where it would change. And somehow this got mixed down below. This was of that upper stuff. Wanted to point out, this is another one of those upper Resurge things. And this, it almost like people say, well, it looks like concrete. Well, that's where that becomes denser, and therefore you get the velocity change to give you a seismic image, a line there, reflection, and then it would be finer grained above that. Now, just to give you, I wanted to throw in these, especially since it's mineralogy, a mineral group. Thanks to Wright Horton, he made some beautiful thin sections of the core. And so here you can see planktonic foraminifera. There's dolerite clast with plagioclase and its dark altered proxine and mesostasis. I'll just keep going through quickly. Here's actually showing crystalline clasts over sediment clasts, and you start seeing things. And what the main thing here, there's a lot of different things being shown. Volcanic matrix is these melt fragments and shock fragments along with these, where we're getting more crystalline clasts. They believe this right in here represents the final plume coming down, where we get so much melt and shock clasts, and that's the end of it. And then it's clearly just Resurge moving things around. Again, here's more thin of just slab sections and core pictures of the Exmore breccia. This is the typical fine grained what it is. Here's the matrix, and you can see the glauconite and all these different things mixed in there. Same thing here with a fossil fragment in there. Now this one's just above the swavite. You see no glauconite in that one. This is way down 1,390 meters depth, whereas these are way up 450 meters and stuff. Now, these things get altered a whole bunch. So here's an example of completely altered to montmorillonite and smectite, partially altered particle with vesicles. So the dual alterations fillings, brown remnant mafic precursor minerals is what Wright believes those are. Altered phyllosilicate down here, the brown ground matrix, trit-like silica. And then here, just some more of the same. Here's that impact spherical. He got an image of a thin section of one. Melt shards with Schleren, I believe it's pronounced. Partial melting is what that means of the clast. I'll show you another picture of one that's not thin section. And I thought this was cool, is example of curved fractures. Now here they're showing some pressures. They've got data from the petrography that suggests pressures up to nearly 50 gigapascals, and a bunch of them in the 20s and others down in the 5s and 10s like this. I think this is the other cool thing. Felsic mineral class with PDFs. Now, I don't know if that's a very often found thing, but I thought you can see the striations this way and striations this way. There's a class that I found with partial melting. And Uwe Remold, he published this picture that I have. And here's just some bryozoans, some different fossils I put in, planktonic forams and stuff that are in, they're all, you name it, you can find it in these cores. Backscattered images of some of the melt. Dr. Tolo, you may find this very nice, but you may have seen his papers already. His Wright Horton stuff. Now here is down in the, we're getting into the fluidized zone. It's just clast on clast on clast, and occasionally you get a little glauconitic matrix spread in here between. Here you are trying to figure out, you can see the different arrows are trying to show the fluidization and liquid. There's fluidization of these classes. They're banging and moving around as well. Let's see, well, this more of the same. I'm gonna move on. More of the same. More of the same. I just find that here you can see that it's almost solid lignite in between the two clasts, chunk. Variety of colors. They're all, when you study the edges of them, they're very torn up and ripped, and some are pushed into one another, and clasts have clasts inside them, they're smushed in. And now here's a contact. When we came down to the bottom of the sand, we came into this granite. Unfortunately, the granite went on forever. I think it was 300 meters of granite. So they, as I said before, they wanted to shut it down. That's a close-up of the sand on the granite. And granite near the top looked like this. And you get further down, looked more like this. They put these hard rock guys like to put marks on their core. This was important because when people pick it up, they won't put it back wrongly. You want to make sure which way's up. So red on the right, blue on the left. A lot of the people laughed about that because all of a sudden you're photographing. I wanted them to wait until after I photographed the core, but there was arguments about that. The basal red, because it was partially heated, is what the argument was. And here's some of the nice, at different places you had fine-grained biotite granite, then you had medium to coarse-grained biotite, and then you had gneissic biotite granite. There's a close-up in the washing shell, so it looked nice and clean. There's more of the granite going down. And then here's how nice and red the ladies, the rich ladies that would come, they say, oh, I want a table of that. I say, well, you better bring a lot of money then. It's going to take a lot. And there you can see it being contacted with the sand over here at 4,498 feet. And That was a great day. I walked on air when that pulled up. Lucy had just gotten back to the site that day. She'd been away, and so I was fighting with these guys. They were definitely going to shut it down. And I might have been able to squeak out another day or so, but they were ready to, everybody was clamoring it was a waste, and we'd run into a block. And they were telling us that they believed that especially Christian Kerbel and one of the geophysicists was arguing that our interpretations of the seismic were totally wrong, and it's a much smaller crater, and so on and so forth. But just an example of this lower part, we go into this sand, and then we hit this amphibolite block, more sand, and then we go into the cataclastic boulders, and this doesn't even show up, but the swavite's just down below a little ways. So there's that sand and the cataclastic boulder, close up of the sand and that boulder there, you can see. We get to the swavite. Now this where everybody really got excited, and so we actually got some more money from NASA Directorate because we ran out of money right when we hit this. And I was soliciting, you name it. I had one guy that was a car dealership guy down in Virginia Beach offered me $20,000. I said, no, that won't pay for one day. I need real money. Anyway, let me show you a close-up of this lithic swavite, this lithic breccia and swavite mixed. So the dark black is melt, and the grays are melt, and there's a wide variety of melt and glass. There's lots of different stuff to study in this. And actually, you can see clasts that were faulted, fractured. You can see all the different varieties of rock fragments that are in there with the melt. See, these are melts, this, and these are clasts. There's melt shooting along the edge of it. Another type of, there's in the more melt. What was neat was I saw these cores come up, and I saw them all change quickly. Here's a little where it went into you get the melt. See if I have the close up. Yeah, you can see the melt going into this cataclastic rock, clast. Then here, I don't know if you can see it. See this greener color here? That was pure glass, very translucent green when it first came up. And I cleaned it up and photographed it as quickly as I could, but it changed color so fast. And what it's doing is actually turning into clay. As you come back and sample this core a month later, and you just see clay there. You just see gray. And this was beautiful green glass right there. Various clasts here. I'm taking too long. There you can see a little bit of the glass still left. Hadn't completely turned. There a little bit more. But that's a thing that I would always propose. If you ever work on something like this, or you have an idea that something's going to change quickly, have refrigeration units that you can quickly put the core into and keep frozen. Close up of the glass, close up of some of these melting in a matrix. You can see how they're tossing around. This one didn't come out so well, but I've got close-ups of the glass where you see at the edges how a lot of melting of the matrix along the edge. Get impact melt clasts and shock quartz, beautiful stuff. More of the melt. Here's the bottom of the hole. We ran into schists and pegmatites.
You've gone down from 30 people to 20 people.
Okay.
So we're way down to 5,000 feet, and see this. I'm almost done because I'm not going to hit on the effects other than just mention them. Well, I guess I'll show some stuff, but these are just pictures to show this pegmatite. You can see a chlorite filled fracture right there. Now, they say these things are not shocked, and so at first they tried to argue that, oh, this was the basement, but they actually do have some melt things that fracture into them, And based on the seismic data, there's just no way that that's the basement. That was the bottom. I think there's a whole nother story down below. Here's some of the mica that actually shows some of these planar deformation features, we believe. Possibly, and there's some more close-up of there's a little bit, I put this in there because here's some of the matrix, the melt, down in this stuff. And then this is what we ended in, beautiful pegmatite. Matter of fact, we went through, at that point, they said that the ones who know pegmatite said it's the thickest section of pegmatite they've ever seen in Virginia. So here's the little lesson of experience, predicted depths. We started and we had trouble. We had to abandon or deviation in holes. Rods would get stuck. Everything costs more money. In the Kiptopeke, we did the same thing. So everybody plants rods in this stuff. You got it. It's very tricky. And one deep hole isn't enough. So very quickly, I'll talk about, I'm going to skip this. That was another summary. This was from my 1999 paper without the black faults shown on it. And this is this being the central crater, and had all these mega blocks, and they were saying you could throw this all away. And we drilled over here at Langley. And from that moment on, as everybody's right here, we drilled the Langley Corehole, and it proved this stuff. So I made this lithostratigraphic framework, and it was from doing all of this work prior to the drilling of this and prior to our project, doing this work over here, was that I was able to convince the Hampton Roads Planning District Commission to, actually, they funded me, and then they wound up funding the project and helped make it so that we could get the project. And they were tough. They had their consultants telling them I was not right. This is some faulting on the south side where Dismal Swamp and Portsmouth. The best way to be able to draw lines between one core or the other is to actually have it faulted. And then subsequently, we found even more faults in there. This was the only fault that I've ever cored, and it was at the Langley, NASA Langley Corehole. And you can see there the fault gouge, and it was within the Chickahominy. And sure enough, it wound up making the Chickahominy section get repeated. Now, there's a big groundwater story. I won't go into this, but you can see the fresh water's out here to the left, coming down here, and it gets to the edge, and it's got to go up and over or wrap around it. It's our ideas. And the hydrologists still like to try to combine these layers with what's on in here. And when they put some wells in over here at the north site, I made them bet it wasn't going to be anything. Out here, they'd get real water. It's a great aquifer. In here, they got a couple gallons, and that was it. Because it's compartmentalized. The water's not moving around inside the crater. Matter of fact, they found out it says the textbooks can be thrown away because they found one piece of a clast with fresh water in it, pretty much, and right next to it, a clast with brine. And through all these years, there's been no equilibration. And there seems to be no head to move anything around. The last time stuff was moving was the hydrothermal activity that lasted tens of thousands to 100,000 years ago. And there was people that studied that. If you get to this, if you ever get the professional paper, the special paper on this, it's got sections on the people that studied, you name it. They were throwing the kitchen sink at this core. Anyway, the salty groundwater story, I'll just quickly go down here. There's the crater, the pumping center, so the water's flowing in the opposite direction. And we thought as a differential flushing hypothesis was good. And they've built these desalination plants to the west of it. And what's interesting is inside the crater, inside this really salty water, that they found a bunch of it that they did isotopes and studied a whole bunch of aspects of the water by squeezing the cores and getting the water out of it. A lot of painstaking trouble to do that and make sure it's not contaminated. And they found that they've got a lot of the salinity is inherited, and it was probably 100 to 145 million years old, and it's probably the oldest sizable body of seawater to be identified like that in the world at this point. There's actually earthquakes that wrap around the edge as well. I wanted to just put that in there. These are modern earthquakes. And so it's still faulting, and you truncated all the marine aquifers. So everything's different inside the crater. So back to the salinity. They've been age dating the water, and it ties into the James River structural zone. Sure enough, north and south, another difference again. And you get fresh water about to here, and then now you know up to super old water in here. So we did all this stuff 40,000 years. Let me get to the next one. This is just about the hypothesis again. I didn't want to belabor that. Here, just quickly go through these. So we squeeze the water here's some of the different things we actually use. They use chlorine 36 as an age tracer, which is pretty cool. And they looked at various isotopes of chloride, bromide, and iodide. They came up with that older age. And we put them in inert gas so they wouldn't react with anything. And they would squeeze the water out of it. And so it developed a method in the 70s. So putting these things together, you can see how the salinity increases into the crater and downward into the crater. Now, last but not least, there was a biosphere study, and so we took samples and great pains to put in little fluorescent beads. We'd have put them they were in a bag, a little packet that we put into the core catcher, so it would break just as it was coring this new 10-foot section. And it was also a chemical they put in that they would get trace. Anyway, these are the results. This is the groundwater. You can see how saline it got as you went down. And this is where they didn't do much with the granite block. And that's also where they didn't find any bacteria. But this is the ones they believe actually worked. Oh, and they tested all the stuff. So these are all carefully checked that none of this has any contamination in it. We actually had a hood on site and did all the work inside a hood. We did it as soon as the core would come. It would not get washed or anything. We take it in and cut off the mud under the hood and put these things into their containers right away and label. They were able to culture these bacteria. Here they are living. They like down here in this is like a smorgasbord of food down here with all these different things available. The only thing they didn't like was the saline-rich granite. Obviously, it affected all the units, cut them out, the ones that were pre-existing. I could have put a lot more in there than these that were pre-impact. And then the post-impact, there's ones that are only found close to the crater or within it, and other ones where it thickens into it greatly so. And then in the last, we got the Quaternary to the present, which is the story of the Chesapeake Bay, because it's a drowned river system. All the rivers turn when they cross the edge of the crater towards the ocean, towards the center of the crater. And they don't go over the central uplift. Here, I'll show you in this image right here. Here's the central uplift here. And these are the various Susquehanna River paleochannels. This is the one only recently discovered. I actually augured a hole over here at the Persimmon Point pit and discovered it when I was helping lead a field trip with Bob Mixon. And so we had an inkling of it, but then with subsequent drilling, these question marks can show, basically it's proven this comes through here. So this is the oldest one. Then this one came down, the Exmore paleochannel. Then this one, I think it's the Eastville, goes through Eastville, and then the Accomack goes down. So they all go in and get their out. So that has a relationship to the Chesapeake Bay. So people ask, well, how come you have land over here if this thing is still subsiding? It's controlled the bathymetric low, topographic low for as these rivers have developed over the last several million years, 4 or 5 million years or less, and mostly the last 2 million years. And part of it has to be explained by longshore drift. There's so much came off from the glaciers that you've been able to spread the spit on down here, but you also blocked off the Susquehanna from going out to the ocean here by the Hudson Delaware River system that deposited the Bridgeton and then the Pennsauken gravel, these big gravel sheets with big boulders and cobbles and stuff. And the mineralogy proves they come from they include the Adirondacks rocks. So this wasn't put in here by the Susquehanna River. So the Susquehanna River, the data all shows it's been coming down here and not able to get to it. It goes here, and at that point it's captured and goes down to the, and all these are all are just tributaries to it to get out. So with that, I thank you for your attention. And I don't know how, I didn't keep a clock close to me. I know it could be 10 o'clock is all I know. One last thing before you start with the questions is, this will take a second. Scott Bruce we do a lot of different ways of modeling, as Lucy showed you, and I was explaining it to a few of the people at the beginning before we started, but he built this really cool thing for a whole big school, and he shot a projectile coming in. That's the comet, supposedly it's going to land into this and give people an idea what happens. And he shot it with an air rifle. And so here you are, you're making, that was our 30-mile splash, filled it in, and that's it.
Excellent.
Oh, thank you so much, Dave.
Now I'm back. Are you the only two still here?
No, there's still some people here. Thank you so much.
It was hard to pin down on. I know I was rambling on, but I thought you guys would rather see the thin sections than the more of the story about the interaction with all the scientists, because there was debates the whole time about everything. We were always trying, and we were, we're not impact craters guys. We were learning as we were breathing, and so I spent a lot of time reading.
I just had a fun time looking at all those pictures of those people that I knew.
Oh, and the
way back
people.
when.
I decided I had to keep the people in. I would have liked to have. I could just sit here and have gotten a picture and this one did this and this and this and this and this. Like I don't think I was a picture of Wright Horton. He's one of the main guys.
Right, I didn't see Wright, but I mean Jerry Johnson, you got him in there.
Jerry was paramount. He let me stay in his place.
He knows Jerry.
I'd be driving from up here to the drill sites often and back each day. And Jerry would let me stay at his place because there was no support for me. I mean, I was labeled crazy, wrong, and fought with almost on every step. And then when I got the real proof, then you had people come out and say, oh no, he was just a driller and they didn't know what they were doing. I'm the one that discovered it. And so it became, what's funny is the truth sort of came out on its own, and as it should, because it's not, the least important thing is who discovered. It's that you discover something. And it's more exciting that I like this moment, I would rather go keep working on it. There's so much we don't know. And there's a lot of core available waiting to be worked on. The core's out there investing. Go get it.
Is that in your sights, is to still work on it some?
Oh, I want to publish the seismic data that we never got out. We only got a little teeny bit of all that seismic money and work. To me, that's one of the accountabilities, but I'm working on Washington East almost every day, except the last week I've been doing gardening and stuff. Trying to get outside. Actually, they're fixing fence, plumbing. I spent all day Monday, I was doing plumbing here with the plumber. So I had a flood, the basin flooded. Oh, you don't want there's always something new. My wife had a flat tire today. She couldn't reach me because I left the phone in the wrong room. I'm really good about leaving the phone in the where I am not.
Well, say hi to Meredy, please.
Will do.
I
I'm
haven't
answering
seen
the
her
phone.
in years.
All
Ah,
right.
Can I ask a question?
Please.
If you were to model how the topography was before the impact crater and overlay it with how it is today, would it be the land masses, would they be in any different area than what it is today?
Let me see if I'm understanding you. You're asking me if today,
Like
if-
before, if you go before the impact happens, okay, and you drew a map of where the land and the seawater and all of this were,
Mhm.
as compared to today, and you overlap those two, are they pretty much the same, or it has changed a lot?
It's changed quite a bit. When it happened, the sea level was, the shoreline was someplace west on the Piedmont, someplace west, we don't know. There's no record left there. What's interesting is our drilling in further north up on the northern neck. You don't even have to go that far and you don't even find anything left of it. So
Right.
erosion has clearly done a lot. I think the waves probably pulled a lot of it back into the hole, and then what was left got eroded by the next subsequent. You had high sea levels during the upper Eocene, so Chickahominy. In general, the basement would have not been any different. It's buried way down there. And I didn't mention that. That was one of the things I was going to talk about, was that we hit it. That was that one main cross section at the very beginning and later on. We hit a very asymmetric target. The basement was dipping to the northeast where it hit. And so you're looking at everybody thinks of, oh, it's all dipping towards the ocean. The tectonic low is to the north. And so if you do, I've mapped the basement, and sure enough, and the Norfolk is considered an arch, the Norfolk Arch. And I think part of that arch is that this crater reactivated the structure there. Because
Okay.
so you actually did, it would be hard to believe it didn't affect some faulting. But because it was a asymmetric target and you had hard crystalline rock overlain by pretty dense Cretaceous delta sediments, and then a thin marine, Paleocene marine section. And then just before the Chickahominy, you actually did get limestone. So we do have limestone clasts lying around and everything. You had the Middle Eocene Piney Point, and but that was being buried by the Chickahominy, and we do have Chickahominy. So part of the Upper Eocene was in existence before this thing hit. Well, that it happened during, and so we have a class of Upper Eocene sediment within the breccia, not just little pieces. In other words, we're finding the Upper Eocene dinos and forams in the matrix, but it's very rare to see the class. But we find a class of, I think it's 12 different units, coastal plain units that are in there.
So you
And
don't
then
you don't have like too much tectonic movement before to now, kind of, from where it was before.
No, that's the beauty of this crater, because and that's something I wanted to point out was every time we core the Exmore, when we go into it, the top is the same. It has that fining upwards clay, sandy, blah, 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 a little fining upwards package, but then it gets up to that top chicken wire clay, I was calling it. We see that each time, and it's different thicknesses, but we see, to me, that says you haven't eroded this thing. The biggest of changes we see is where we drilled right on the edge. And like I said, we have a slump and a faulted section of Chickahominy. And when you get close to that outermost rim, which is, 56 miles in diameter, not the inner crater rim, we know so little about that other than the seismic data.
In one of the publications that you show, one of the people there was Kenneth Miller.
Yes, Ken. I meant to mention his name.
Is that a paleomagnetist? The paleomagnetist Kenneth Miller?
Yes, and he brought a
San Luis
whole
Obispo.
army of guys. He's one of the authors in here big time, and he's one of the editors because he's one of the big wigs. He helped bring
Yeah.
a bunch of his students, and they wrote papers and published and really worked hard. His Browning, actually the student that published one of the papers that I'm in with, I actually gave him all my stuff on Exmore, and he did a great job. He got a job with the oil companies like immediately after he graduated.
Yeah, yeah.
He's got a lot of his guys in the oil patch though. But
Thank you very much.
Ken was doing it. I still communicate with him. He's fabulous. Well, when I say still, I haven't communicated hardly with anybody the last few years.
Yeah.
I'm
I mean,
buried in,
I mean, he was in St. Louis Obispo when I was in California.
oh
I think.
yeah.
Yeah, because he did some paleomagnetism work that I did too. Yeah.
He does that, and he's really good with the students. He really has a little
Yeah.
good army.
Exactly.
And I've worked with him up in New Jersey. He's one of the guys I would be up there with our drillers and stuff. And at one point, I was the only licensed driller up there. I have a New Jersey's driller license, which is not easy to get.
Yeah.
But they had to have me on site because I was the only one really licensed. And then we won a battle that the federal geologists don't need to have their license after I'd already gone and gotten it. It was a hard exam. It took me like 5 hours to pass their exam. It's one day I sat there. And they told me there'd be no stuff on hazmat, and it was about a third of it was hazmat.
Thank you very much.
Oh, so it's a very interesting story. The actual crater wouldn't have looked, if it happened right now, it still would be the same story, to answer your first question.
Thank you very much. Thank you.
So Cindy, thank you so much for finding David. Roadside Geology 2010 edition. The only page that I have earmarked of interest is the crater. And it's Powers and Bruce, 1999. So thank you very much, David Powers.
Thank you so much. I haven't seen that. I'll have to get that.
Yeah.
I have the old ones.
The old ones here too.
Yeah, there it is. Yeah, exactly. I have a whole army of those. Those are great. Whenever you travel, you got to have one.
Yeah.
Changes everything.
Dave, Kathy she is big about she volunteers at the Natural History Museum down in the mineralogy department down there.
Cool.
And we have a couple members that do that, but I know Kathy, lots of educational programs for kids in schools and things like that. So.
Oh, I love it. Well, I grew up in the Smithsonian because my mom worked there. So I used to go to the openings. She used to hire me when I was old enough to think, and she would hire me to help edit. She was a scientific editor.
Wow. Well,
she left there and was at the National Geographic, a research editor over there after she retired. But she was at the Smithsonian forever. I love the Smithsonian. Smithsonian's the best.
Yeah, a number of our geology colleagues, volunteer geology group, we have an affiliation for the last like 40 years with the Smithsonian.
Oh, wow. So that's cool.
They've been very good to us.
Oh, I bet. Oh, I love the Smithsonian. And I've given a lecture in the Natural History Museum before. I've been in that. I've given one. I can't remember who. I've given so many lectures, I don't remember who that was or when.
You knew Scott, what was his name? Scott Woodward or Wood? He came and talked with us one time. It was when we were meeting at the Smithsonian, because we used to meet there pre-COVID. And what was his name? He was sedimentology, mapping. Lucy, you know him.
No, I'm sure I do. I'm trying to think.
Anyway, just thank you so much. I just, how many, was trying to keep track of how many studies, tests and studies that went into this project, and I lost count. There were so many.
I was amazed how we had, I forget how many, I guess 60 at least, or 70 major scientists, and then their students. There was a guy named Yuri Popov who came from Russia. I didn't even mention, they did such incredible studies, physical characteristics of the core. that they actually took that along with other people that did it. And they were able to fill in a lot of stuff that we didn't get from our logs, because we didn't do a full suite of logs. We did the basics, and they had trouble with the logging and stuff. They always trouble with something. And they, this guy, Yuri Popov, that was another thing that we did, because we were the hosts. We took samples for everybody. They would come and say, look at the core, and then say what they, give us a list of where they wanted them. And then we would take the samples. And I think for Yuri, I must have sampled several hundred samples for him. And so we became friends, and he used to be in charge of the entire nuclear program in Russia. And so he would say, David, sit down. I'm going to tell you a story. And he'd tell me all about, they've been drilling a hole over there since the 60s. The same hole, they're still drilling it. And he says they made a Christmas tree. He says it's many, many miles deep, but they drill out to the sides from it all the time. And he said, you have to come over. I took him out on the bay fishing, he and his students, in my boat. I had a boat in those days. And we caught food and he ate it. He had I met all these different ones, all the people, the Germans and their students, and the Germans work their students as hard as anybody I've ever seen work them. And the guys from South Africa, Uwe, I was lucky enough to get to go to South Africa and go see the biggest impact crater. Oh my gosh. That was one of my highlights of my life. That was because I don't travel much. I'm always working. Vacation doesn't mean vacations. Time to get some
ships. Well, I see Lucy's joined us. Hi, Lucy. I see you're muted, but
hi, Lucy.
You're on.
And Richard Tolo.
Yeah,
What a great pleasure to see you.
unmuted now. Yeah.
Richard was my professor as well. I have a great fondness in my mind of Richard. Hey, Lucy, how you doing? You look good.
My grandson was the Energizer Bunny in the first and second grade show, so I was a little bit late.
Well, that's okay. I just wanted to let you know I'm going to call you soon. I have been doing a lot of work on Washington East.
Good.
A lot. The saddest thing is I compiled so much that I'm not sure about the faults. Some of the ones. The main one over there, it's at the point of almost like the crater study. We need another hole.
I don't want to hear
all I do is every time I go there, I go, can't get a hole. But we really need one to the east of Easton. No, to the west of Easton.
Well, give me a call. You got my cell.
Yeah, you bet. Sorry to do some business at the moment. I haven't seen you in a long time.
It's great that Lucy showed up, because Lucy's the one, I know that you and Cindy go back, way back, but Lucy's the one who also gave us a little preview of this. When you presented to us, you remember, regard to the fossils and so forth, of the crater impact. So this has been absolutely marvelous. It's wonderful to see all the scars and brutality that you had to experience, David, when you're trying to change a massive scientific enterprise, because we read these aspects of people in history who had to do that, the map that changed the world with regard to canals and so forth back in England, and the class battles that they had to fight against. And here you are today, having gone through this. And thank you for sharing all, this is only a part of it, but for us, it was a great deal of information. And we really appreciate your putting it together. It's been marvelous.
Oh,
so thank you very much.
I love talking about it. My problem is I can't stop.
Joanna?
Can I ask one more question, please?
Absolutely.
Since you brought it up, I assume when you said Africa, you meant the Vredefort impact crater in South Africa. Okay, so this is something in the back of my mind that I always had it because of my gemology also, togetherness thing. Do we know at all if that impact crater influenced any of the cratons that they are diamond bearing, like the geology of did Do we know any about that? Anything
Yeah, well,
about that?
they argue that the crater actually uplifted so much that it actually lifted the I can't remember if they went as far as the mantle, but it uplifted so much that that's why they can actually mine for those things as deep as they are, because it's lowered the temperature of that stuff. Actually, they argue that because if you go down, it gets hot fast.
Yes.
And I didn't even mention we had crater water coming out of the well when we pulled up and left, and it was running and it was warm. It was actually we have one guy that in that volume just talks about the temperatures and that the temperature is way too hot. It shouldn't be that hot. And so the owner of the place was thinking about, oh, he could sell crater water. And then he was making some measurements, and one of the students dropped the probe down there. It stopped flowing. It fell how many thousands of feet? I don't know. Because we have a couple of different types of rods planted inside themselves over there. It's kind of sad. I hate leaving rods in the ground, but we've done it everywhere. Don't have to be in the crater to leave rods in the ground.
So it may not have been the reason to create the big cratons that they bear diamonds, but it may have been the reason that uplifted the cratons to make it easy for us
so you could get to it.
dig
That's
and
what
find.
that's what I remember, because I was impressed that they were saying that.
Okay, but it was not the creator.
Not that it lifted it up, although there was some, they talked about the tectonics like that some. Maybe that's why this whole thing here, and that's why there's a dome. They argued whether there was people thought it was a dome and just an eroded dome, but it's got some of the most beautiful breccia where you can go and see a whole side of a hillside that's just this
exposed,
unbelievably beautiful melt breccia. They showed us where they slabbed it I was just trying to, how can I find money to get one of these, 10-foot long, 5 feet wide, 6 inches thick slab it polishes up beautiful. Because I'll never get to down in the Chesapeake, obviously, but there it's just a matter of getting it from there to here. And they were saying there was one stuck up in Canada in Mail that nobody was claiming. And I was always like, I'll go get it. I'll do that. But I still don't even have money for that. I'm not a money guy. I don't think about money. I just want to be able to do the job, and somebody will show up with cash. I'll do it cheaper if I can.
Thank you very much again.
Thank you.
Very much. I thank everybody for coming. It was really a marvelous evening. David, we really appreciate it, and hope you can keep on cranking out the questions and your discoveries. It's wonderful.
Well, I was torn.
Thanks.
I was almost going to talk to you all about the mapping I've done in Washington, D.C. That was the last thing I was doing before, along with the Washington, D.C. East. And all I can say is you have a lot of faults that no one knew about, and the drilling that they've done and all the investigations they've done for the new
African Museum?
No, for the much more all over the city for the new, is it sewers? Yeah. The new things they were making such big tunnels that they were using those big billion-dollar things that go down.
Mm-hmm. Yeah, I know what you're talking about.
I have so much information on that, but before I got to work with those guys, get there, and I got to look at these drills and stuff, and they have so much data, but I was already mapping all this stuff, but I mapped the faults, but the paleo channels are all over. The city is underneath. You can, if I was going to show the image of this stuff, it's amazing. And then Washington East has got these cool things that make no sense at all. We have, in other words, I'm back to like I was at times in Southeast Virginia, where you draw the cross section, but the dips on the beds are too crazy and the units change too quickly. And so Jerry Johnson was the one who was planting the seeds in me. Try drawing it with a fault in between. I do that. I was like, oh, it works. Look at that. Look at that. Look at, oh. And so now I don't run to a fault because I still like, no, I want to prove it. But we have such different packages over on the Eastern Shore and things missing in the middle at Tillman's Island and everything's more back to the same overall on the west side of the bay. But then I've been working with Wright Horton up. We're still trying to get this basement map of the Mid-Atlantic out. Should have been out like this Washington East map several years ago. And the new rules on that you have to go, everything's got to go digital. Everything has got to be digital, and the metafiles have to go on for 1,000. They want you to describe every little segment of every line on that map in all the metafiles. And they want a lot of information on, well, what degree of confidence do you have? What was the on and on and on. I told him, how many lifetimes do I get to do that? Because it's ridiculous. It's ridiculous. And then I said, who's going to read this ever? And then the GIS guys just say one thing and repeat it over the whole thing. I go, oh, then it's worthless. So I'm still playing with some of those things, but I leave the metadata to those metadata people. And I keep working on the real data, which the puzzle is always so fun to work. As I work these logs and you go back and forth, I think one of the most important things that I did in discovering the crater was looking for patterns. And that's what I saw in the data and in the well cuttings, looking for a pattern of what I would see and describe. And then I would relate it to the one hole that I have. I say, well, that must be that, and that, and that, and that. Because without a core, you're just matching squiggle to squiggle, as if you're just chasing aquifers or confining units, and they can do that quite well. But real formations, different story.
Okay, on that note, thank you very much, Dave, for sharing. And there's down the road, we'll maybe hear more from you. Thanks very much. Good night, everybody.
Good night. Thank you so much. Good luck to everybody.
See you, Lucy. Bye, everybody.
Cindy, it's so good to see you.
Thank you very much.